So looking at forces, remember for forces, what were our tools? Free body diagrams and Newton's laws. We really only had three equations. It was F net equals ma. That became winner minus loser equals ma. We had weight. The force of gravity was mg, which technically is ma in disguise, where g is the acceleration due to gravity. And we had an equation for friction. It was mu times the normal force. We introduced the concept of the normal force, how hard the ground pushes up, also what a scale measures. So example 3 says a 75 Newton. Ooh, what did I just give you when I said a 75 Newton sled? Did I give you its mass? What did I give you? No, now. I gave you its weight. So this is mg, which means I can find m. I might make a little note here. M equals, it's going to be 75. How do I turn newtons into kilograms? Yeah, in other words, to get the m by itself, divide the g over, because the g is multiplying. So I'll divide by 9.8, and I'll probably store that on my calculator, because I don't think this is going to work out to a nice number. Maybe it will, but I'm doubtful. 75 divided by 9.8. I'll make a note, 7.653 maybe. I don't want to round off too much. I wouldn't say 8 kilograms, even 7.7. That's going to introduce a lot of error into the rest of my calculations. A 75 Newton sled is pulled across the snow at a constant speed. A horizontal force of 85 newtons is exerted to keep it moving. What is the coefficient of friction? This is already a pretty difficult question. I would consider this probably a C plus B. I'd call this a B level question. There's a key phrase in here that's going to make this slightly easier. Ryan, what do you see as the key phrase that's going to make things slightly easier? If it's at a constant speed, what's my acceleration? And that means forces are, everybody, I'm looking for the stress letter B. Okay, this is going to be a job for a free body diagram. So here's my sled. What are the forces acting on it? Martin, get the obvious one. Is the sled sinking into the ground like quicksand? No. Is it flying here like Superman? No. And in this case, I think the normal force is the same size as mg. So later on, I'm probably going to say, I don't know the normal force. Oh, but look. I don't know the force the same size as the normal force. What else? We have this horizontal force of 86 Newton. Who remembers, what did we call the mystery force coming from off the page quite often, because we don't want to make up a backstory? Yeah, we called it F applied. That equals 86. By the way, I guess I could even put the 75 right there, which means the normal force is also 75. It's got to be. Why can't this be correct? Why is this impossible based on this question? That can't be going at a constant speed because forces aren't balanced. Jacoby, which way do I need to add an arrow? How big? Yes. There's friction. That doesn't quite look the same size, but it should be the same size. In fact, I can even say friction is 86 newtons in this case. Now, if there was an acceleration, that would raise this to like a B plus A minus level question. Then I would have to do a full winner minus loser. But in this case, because it's a constant speed, it's a tie. I could go, who's winning? No one's winning. What I can really say is horizontally, friction equals F applied, where F applied is 86 newtons. They told me that. Friction is what times what? So I could say on the next line, mu times the normal force, and they want me to get the coefficient of friction by itself. You know what they want me to get by itself, Renat? The mu. What's the normal force doing to the mu, Renat? Adding, subtracting, multiplying, or dividing? How I'll move it over then? And so I'm going to divide by the normal force. I don't know. Oh, yes, I do. The normal force is 75 newtons. It's going to be 86 divided by 75 newtons. I've made up a terrible question with terrible numbers. I'm going to have to change this next time because we're going to get a coefficient of friction bigger than 1. On snow, it should be like 0.1. We're going to get a huge nonsense coefficient of friction. I'll change that for next year. I made up really dumb numbers. To keep this going at a constant speed, I probably only need to pull with 8 newtons, not 86 newtons in real life, because it's easy to pull stuff on snow. So I apologize for that, but it would be 1.15, which, I hate making up dumb numbers, but clearly I did this time. This irritates me. And that's what they wanted us to find. Normally, coefficients of frictions, again, are between 0 and 1, and if the closer to 0, the slipperier it is. Snow is slippery. Should be like 0.1, 0.15, 0.2 maybe. So I feel bad for this one. Sorry. An object with a mass of 32 kilograms has a weight of 528 newtons on a certain planet. What's the acceleration due to gravity on this planet? Okay. They gave me the mass. They gave me the weight. Oh, my equation for weight is mg. Now we're on a different planet. G is not 9.8. Evoluna, they want me to get the acceleration due to gravity by itself. How would I do that? How would I get the g by itself? Because that's the acceleration due to its gravity, this mystery planet's gravity. How move the m over? Yep. Yeah. We call this gravitational field strength. So it's going to be the force of gravity on the planet divided by the mass. Remember, mass is the one that doesn't change. It's constant anywhere in the universe. Wait, no, now that's the one that changes because it depends on what planet you're on because of the g. What's g on Earth? 9.8. What's g on the moon? 1.6. G on Mars? About 3.3. So this is a mystery planet. It says the weight is 528 newtons. It says the mass is 32. Let's find out what the acceleration due to gravity is on this mystery planet. I get 16.5, probably a bigger planet than Earth. Am I wrong? Not newtons, Mr. Dueck. Thank you, Mason, for giving me the stink eye there. It would be meters per second squared, because it's an acceleration, or you could say newtons per kilogram, because we did go force divided by mass. That is newtons per kilogram. These two units actually work out to the same thing. B. Mason, what does B want me to find? Oh, that's easy. The weight is mg, so it's going to be 125 times 9.8, right? Oh, we're on a different planet. It's going to be 125 times new gravitational field, which is 16.5. Let's crunch that and see what we get. Pause the video. Got someone coming in late. It's going to be 125 times 16.5. Do you get 2062.5? I'll go 2060 newtons, but if you wrote the whole thing, that's whatever. Your test is multiple choice, so that's the one you would pick. I'd probably go to 3 sig figs. Turn the page. This I would consider a solid A level question, and the reason is there's an extra vertical force besides mg. I see friction. I see an F applied. So it says, given the following situation, find the normal force, find the acceleration. You know what? Before I even start, what might this be a good job for? Yeah, I'm going to do a free body diagram. So did they give me a picture? I'm going to label the picture right on here with my forces. What are the forces acting on this, Sienna? Get the obvious one. Which way? Yep. So I'll put that there, mg. What else? Are we sinking into the ground like quicksand? No. Are we flying like Superman? No. So there is a normal force, but you notice there's an extra vertical force lifting up. That's not the normal force. Because someone's lifting up, the ground isn't having to push up as hard. The normal force is going to be smaller than mg. If someone was pushing down, did I do it pushing down? No. If someone was pushing down, the ground would have to push up harder. Then we have F applied. Oh, there's a coefficient of friction, so I should also add Sienna, there's friction. So A said, find the normal force. Did I give you lots of space? Maybe. I'm going to do part A, I think, right over here in the margin over here. Sienna, back to you. Are we sinking to the ground like quicksand? Are we flying here like Superman? Normally, I would say, I don't know the normal force. Oh, but look. Except here, it's a bit more complicated because there are extra vertical forces. What I can say is everything down has to equal everything. So everything down in this case is mg. Everything up is the normal force plus and the 36. If I was pushing down, then, Jamie, I would have mg plus something equals the normal force, which is kind of easier because the normal force is already by itself. See, I got to get the Fn by itself. How do I move the plus 36 over? Yeah, how? Yeah. The normal force is going to be mg minus 36, and I'm going to go straight to numbers. M is 12. I'm going to go 12 times 9.8 minus 36, and I'll carry all the sig figs. I get, double check me, 81.6. So there's part A. I would have to do that if on a test I gave you this one. I don't think I gave you one this tough. Oh, sorry, that's a lie. On your final, I did ask you to find a normal force that isn't mg. Probably half of them will have something pushing down, half of them will have something lifting up. But I don't think I added the part B. Part B says find the acceleration. I did this just to review the fact that we can handle it. If we are accelerating, we're probably accelerating to the right. So Claire, who's winning? Losing? You think friction's winning and F? Is that correct? I think maybe, now we'll find out if we get a negative acceleration. You might have been right. Minus friction equals ma. Was it Ryan's theorem? Are you the one and you barely showed up on time? Wow. We can get the A by itself, divide by M. I'm going to move sideways to try and make sure I fit this all in. F applied is going to be 43 minus mu times the normal force divided by M. You know what? That's going to be 43 minus what's mu? I don't know what's mu. 0.36. The normal force, 81.6 divided by 12. That'll get us the acceleration. Once you have that written out, go to your calculator. A solid A or A plus level question would be me giving you the acceleration, asking you to get the coefficient of friction, the mu by itself. Let's see, Mr. Dueck, brackets around the top. 43 minus 0.36 times, haha, answer button, close bracket, divided by 12. Sadie, did you get, or Claire, sorry, did you get 1.14? Yeah. Meters per second squared. It's a positive answer, so F applied is winning. If it wasn't, then friction would be winning. I'd do a quick change. I'd make that a positive, that a negative. In a more complicated question, I might have had friction pointing the wrong way, but here we're pretty straightforward. I definitely put an Atwood machine on your test. Okay, this is probably the longest question in terms of the most amount of writing. Jacoby, what's it asking me to find? I can't. First of all, I'm going to find the acceleration of everything. Sorry, I'm going to write an equation for everything to find the acceleration of everything. Why can't I find tension from that equation? Help me out, folks. I lose tension. Wow. Right? I did the stupid joke about the tension deficit disorder. Then I'll find the tension. So to start out, you know what this is going to be a good job for? Yeah. So let's label, what are the forces on M1, Jacoby? Get the obvious one. M1G, because there's more than one mass. What else? Yep. On the second mass, it was M2G and tension. The tug of war is really between the two gravitational forces. Which one's bigger? Which is the bigger mass? So which way is M2 accelerating? Which is the winning force? Don't say M2 because that's not on my free body diagram. Which is the winning force? Help me out, folks. Yes, good. Now, I often, just so I didn't forget, once I figured out the direction of the acceleration, I often just drew that on there because, Jazz, it's easy to lose track and forget. So now we got our equation. We're going to start out walking along the rope. Who's winning? M2G. Anything that ends up pointing down, once it gets to the right-hand side, is going to be winner plus. So then we have minus tension. What about this tension? Is it a winner because it's pointing up? No, follow it, follow it, follow it, follow it, follow it. When it gets to this side, it ends up pointing. So is it a loser because it's pointing up? I said that backwards. It's a winner because it ends up pointing down once it gets to the right-hand side. This one, Lachlan, you might say is a winner because it's pointing down. But again, if you follow it, oh, I don't want to draw on there. If you follow it when it gets to this side, I think it ends up pointing loser minus. What do I have to change the right-hand side to if I have forces from more than one mass? M all. A. Tensions cancel, and then we can still use Ryan's theorem. Get the acceleration. It's going to be 23 times 9.8 minus 16 times 9.8, all divided by 16 plus 23. These masses are fairly close. I don't think we're going to get a big acceleration. If it was like 23 and 22, they would barely accelerate at all because they'd almost be balanced. I know it's going to be less than 9.8, I can tell you that. 23 times 9.8 minus 16 times 9.8, close bracket, divided by bracket. 16 plus 23. Let me know what you get, Jacoby. So 1.75897. I'm going to write 1.76, but you know I'm storing this on my calculator, right? Or if I knew I was going to be doing more than one step, I'd write this down elsewhere. So 1.76 meters per second squared. Not what they asked us to find. What did they ask us to find? Look at an individual mass to find an individual force. So which mass do you want to use? Okay. Which way is M1 accelerating? Which way is the winning direction? Same answer. Which force is winning then on M1? Yes. Which one is losing? M1G, and that's going to be M1A. If you used M2, it would be M2G minus tension equals M2A. You'd have to do a swappy dance to get the T by itself. Here, we don't need to do a swappy dance. We just need to plus the M1G over, which is actually a little easier. So it's going to be M1A plus M1G. It's going to be M1 16A, answer button, plus M1 16G 9.8. Oh, I don't need to put it in brackets. 16 times answer button plus 16 times 9.8. And I get 185 newtons. So you are going to see an Atwood machine on your test. What I'm not going to give you on your final is a missing mass question. I don't know if you remember, we also did Atwood machines with missing masses. I put that on your test. I didn't put it on your final. That was where you got to use that clever Math 9 operation. How many M's do I have? 1. How many? 2. How many would I prefer at 1? And you have to use the GCF trick. We'll revisit that if you take Physics 12. And I think this is the last forces question. Yes, it is. I have several different versions of the test. Some have an Atwood machine, some have this one. These are the two multi-mass questions. Find the acceleration, find the tension. Brooklyn, spoiler alert, what am I going to do first? What might this be a good job for? And again, I'm going to find the equation of the acceleration of everything by writing an equation for everything, and then I'll find an individual force by looking at an individual mass. Probably this one, the 12, because it's going to be less cluttered. Brooklyn, what are the forces acting on the 4.3? Get the obvious one. I'll call that M1G. And I think there's going to be a normal force the same size as M1G. Renat, I'll call that for normal force number 1 to go with mass number 1. Is there a rope? We have tension. Is there friction in this question? And this is going to be pulling down, sliding to the right, so I'm pretty sure friction is pointing to the left. I'll call it friction force number 1 to go with mass number 1. What are the forces acting on the 12 kilogram mass? Get the obvious one. Yep. What else? Yep. A says find the acceleration. Okay. Who's winning? M2G. And then the most common mistake, people wanted to include M1G. Remember, we're only going to include forces along the rope. So I'm going to walk along the rope, which is going to give me M2G minus tension. This tension here becomes a winner plus when it gets over to this side. And friction force number 1 is a loser. M1G hasn't showed up in the equation. It'll show up in the friction portion later, but it doesn't show up in the first section. That equals M all A. Once again, I would stretch it out, losing tension. Once again, Ryan's theorem. So A is going to be M2G minus friction is what times what, Brooklyn? I know the normal force. Oh, but look. Another force the same size as the normal force. And this is where the M1G makes its appearance inside the friction equation, divided by M1 plus M2. I've scrolled down. What was it? 12 and 4.3. 12 times 9.8 minus what's mu? 0.28 times 4.3 times 9.8, all divided by 4.3 plus 12. Oh, I made a typo. Glad I caught that. Insert a times sign. 12 times 9.8 minus mu times the normal force divided by. Brooklyn, did you get 6.49? No? I see people nodding. Yeah? I wouldn't round off to 6.5. I don't need to. 3 sig figs is pretty good. If I know I'm going to be using an answer to find another answer, I usually carry 4 or 5 just to be paranoid. But 6.49, I'm going to store this on my calculator. If I gave you this question, just like the Atwood machine, I said find the tension. If you get this one, I'm just going to say find the tension, and I'll expect you to clue in, Nikki. You have to find the acceleration first. So, Nikki, let's find the tension. Which mass would you go with? Yeah, less cluttered. Which way is M2 accelerating? Which way is the winning direction? Same answer. Who's winning? M2G minus tension equals M2A. That's the equation just for that mass. What's right in front of the T that I don't like? I'll swap you dance. It's going to end up being M2G minus M2A. That equals tension. It's going to be M212 G 9.8 minus M212 times answer button. You get 39.7 newtons. So from last class and today, that's a quick review of forces. That's what I'm going to expect you to know. Okay? If you're looking for a better idea of how I turn these into multiple choice questions, look at the final practice final exam that I gave you today. We're going to work on it Wednesday, and then I would also work on it before you write your final as part of your practice. Pause for a second. Give me 1 second. If you're okay, I want to try and plow through all of momentum for the remainder of class so I can give you a complete review period on Wednesday. That's the goal. So really quickly, key concepts for momentum. Remember, momentum was a vector. So if there's more than one direction, we needed to let one way be something and one way be something. Okay? Plus VE, that's my abbrev, minus VE. You can write POS or NEG. You need to know the difference between just plain old momentum and change in momentum. So if you look at your formula sheet, plain old momentum was just P equals mv. Oh yeah, we had to use P because m was lowercase m is mass, uppercase m something else, already taken. So it's from a Latin word. What's change in? Well, what's the symbol for change in? So a lot of people kept calling either this momentum, it's the change in momentum, which means the only way that occurs is if momentum is changing, if there's a difference. What's another word for change in momentum? Starts with an I. And what's change in anything? I'm going to abbrev F minus I. And so that gave us our impulse equation, which ended up becoming mv final minus mv initial and force times time. Collisions and explosions. If you see a collision or an explosion, there's two masses. That you want to use is the law of conservation of momentum. And then I'm dropping some blatant hints here because I turned these into multiple choice questions. Forces come in opposite. So in a collision between something big and something small, are the forces the same? Yes, in opposite directions, but they come in opposite pairs. What about impulses? In a collision between something big and something small, impulses also come in opposite pairs. Do accelerations come in opposite pairs? Why not? F equals what? The only way the accelerations will be in pairs is if the masses are the same. And this goes to my big rant of why a small car is often so much worse off in a collision with a big truck. Same force, small car, way bigger acceleration. And I've tried to teach you what does damage. Acceleration is what does damage. There was several of those questions on your momentum test, and as multiple choice, and I lifted those and put them right on the final. Alrighty. A force of 12 newtons acts on an object for 8 seconds. The mass is 3 kilograms. What's the object's change in momentum? Remember, change in momentum is delta P. It's impulse. So I'm going to look at that equation on my formula sheet. I noticed they gave me a force. They gave me a time. I think I'm going to use the version of impulse that says force times time, the third version. Evoluna's looking. Yeah, make sure you see where it is on your formula sheet, right? It's that middle one that had 3 equations in one that we said, really, it was a nice shortcut. It's going to be 12 times 8, which is 96. Double check me. And the units for momentum, 96, Mr. Dueck, were kilogram meters per second. The units for change in momentum were kilogram meters per second. But the same units are also Newton seconds, because force times time. If you simplify force newtons times time seconds, you will end up with kilogram meters per second. So you can use them interchangeably. B, Jess, what did B want me to find? What did we find in part A? There's a word in front of it. We didn't find the momentum. I got to be nitpicky. Change in momentum, okay? So we're not doing P equals mv. We're in that middle equation. Hey, that middle equation also said that change in momentum is m delta v. How would I get that? That's the change in velocity. That looks like an A, Mr. Dueck. Make it a delta. Jess, how would I get the delta v by itself? How would I move the m over? Yep. The change in velocity is going to be the impulse, the change in momentum, divided by the mass. It's going to be 96 divided by 3, which is, I should be at 32. Double check me. Yeah. And it's a velocity, a change in velocity, so it's just meters per second. That means that its velocity changed by 32 meters per second. If it was originally going 2, now it's going 34. If it was originally going 10, now it's going 10 plus 32, 42. Example 2, what will the recoil velocity, magnitude, and direction be if a rifle fires a bullet with a velocity of 410 meters per second north? When you fire a rifle, that's an explosion. There's more than one mass. Harmeet, this is going to be conservation of momentum. What did we say for that? Well, we said the sum of your initial momentum had to equal the sum of your final momentum. That was the summation notation that I taught you, which was the shortest way to write that. But really, we need to visualize firing a rifle. I said be lazy but organized. I'm going to use R for rifle. I'm going to use B for bullet. You could also use mass A and mass B, but if I could, I tried to use words that started with it. Easier to remember. So here's my rifle analog. Before I pull the trigger, what's moving? The rifle, the bullet, both, or neither? Be stupid obvious. Neither. So what's my initial momentum? Yeah. After I pull the trigger, what will be moving? Well, definitely the bullet, and it wants me to find the recoil velocity, which does have to be there because forces come in pairs. There's going to be a force on the gun. I'm going to have mass of the rifle, velocity of the rifle. There's the final momentum of the rifle, plus mass of the bullet, velocity of the bullet. Because momentum is mass times velocity. They want us to find this. Okay. Lachlan, I need to move this term over. How will I move this term over? What's it doing to the velocity of the rifle? So, and there's a 0 over here. 0 minus anything is just negative that thing. So I'm going to say, you know what we end up with over here is negative mass bullet v bullet. That takes care of this term. Now I need to take care of this mass in front of the rifle. What's this mass doing to the V? So, and if you don't mind, I'm going to put the velocity of the rifle over here because that's where we're used to seeing the thing by itself. And I'm putting in the vector signs to remind myself I better pay attention to direction. Mass of the bullet, it says, is 0.036. Oh, don't forget the negative, Mr. Dueck. What's the velocity of the bullet, Lachlan? And by saying that, you've just decided north is positive. You could have said negative 410 and decided north was negative, and I would have gone along with it. But if we get a positive answer, that'll be north. What if we get a negative answer? With confidence and authority in your voice. Yes. Divided by the mass of the rifle, 2.2. We are going to get a negative answer. I'm not going to say negative south. After I get an answer, I'll say equals and then south. So it's going to be 0.036 times 410. No, Mr. Dueck, it's going to be negative 0.036 times 410 divided by 2.2. Do y'all get negative 6.71? I need nods. Yeah. So negative 6.71, which is 6.71 meters per second south. That was the explosion question that we looked at for momentum. Sometimes we had an explosion where the initial momentum wasn't zero. We did a spacecraft capsule that blew up into two pieces. And actually, it worked out well because the probe got extra velocity for free. That's why we have multi-stage rockets. The engines lose momentum. Well, then the probe has to gain, or the capsule has to gain momentum. We're okay? So everyone looking out in the hallway, we're back now? Squirrel distraction. I think this is the last, or two more. Car crashes. I put one car crash on your final. Either in the car crash they stick together or they bounced apart. Ooh, what do we call a collision where they stick together? Inelastic. Bounce apart, elastic. Rubber band, bounce apart, elastic. So car A has a mass of that traveling west, hits a stationary car B. If it's stationary, what's car B's initial velocity as a number exactly? What's car B's initial momentum as a number exactly? I made the question easier for you. The collision is inelastic. That means they stick together. Find the final velocity. Okay. Is this a collision? Yes, we're going to use conservation of momentum. Before the collision, what was moving, Sadie? Car A, car B, both, or neither? So I'm going to have the mass of car A, velocity of car A initial. And what did I always do here? Do you remember? Wham! They collide. After the collision, stuck together or separate? Inelastic. So in brackets, car A plus car B, V final. This is the trickiest one to set up, but the easiest one to solve because so many things are either stuck together or zero. Because Jazz, this wants me to get the final velocity, magnitude and direction. What's the bracket doing to the V, Jazz? Adding, subtracting, multiplying, or dividing? So how do I move the whole bracket over? What's the opposite of multiplying? Yeah, even though this starts out complicated, this is probably the easiest one mathematically I can give you. It ends up being the mass of car A, velocity of car A initial, divided by the mass of both of them. That's going to be V final. And now I can crunch my numbers. 2,350. I've just let west be positive. If I get a negative answer, then that'll be east. And stuck together, 2,350 plus 1,400. This is the same physics. Instead of a car, I could make it a football player tackling and wrapping someone up when that person was standing still. That would be, say, if you watch football, if the receiver was standing still when they caught the ball, and then right when they caught it, the defender went plowing through them. That happens fairly often. 2,350 times 26 divided by bracket 2,350 plus 1,400 close bracket. 16.3 direction. It's got to be west because I let west be positive. By the way, that W, since it's after an at symbol, is west. Otherwise, it could be work, it could be watts. I mentioned we don't have enough, hopefully I mentioned we don't have enough letters going around. Example 4. This is probably the toughest type of collision. Here we have I was still nice, and I think on the final exam, I always let one of the objects be stationary at the beginning, just so you had a little fewer terms. But here afterwards, they're both moving. It says it's elastic, they bounced apart. So before the collision, what's moving? Car A. So we're going to have the mass of car A, velocity of car A initial. Bam! They collide. Sorry for those of you on YouTube with headphones. After the collision, Eveluna, read the question. Car B is traveling south, and it wants me to find the velocity of car A. They must not be stuck together. Otherwise, the answer to car A would also be 24 meters per second south. I see the word south. I see the word south. I don't see the word north. I'm going to make a little note because this one's more complicated. I'm going to let south be positive if I get a negative answer, because it's possible car A bounced off and reversed direction. It might have. Then I'll know. Mass A, V, A final. Mass B, V, B final. Final momentum of car A, final momentum of car B, not stuck together. Eugene, what's this asking me to find? Which one? There's three. Which one? There's two. Of car what? Car what? Yes. Wants me to get that by itself. Okay. Hey, this is formula manipulation. Complicated, but still doable. What's going to drop down like a domino? The left side, yes? Mass A, V, A initial. And then I'm going to do my adding and subtracting. I need to move this over. How will I move this term over? Yep. How will I move the mass of A over? Yep. That equals VA final. I'm not sure whether I'm going to get a positive or a negative answer. Let's see. Mass A, 2250. Car A, velocity A, positive 32, minus mass B, 1400. Car B, 24. You know what? It's getting rear-ended. Car B is going south at 24. It's getting rear-ended by car A. So car B is going to speed up, which it... Okay, so no, car B was stuck still. Yeah. Sorry, I'm visualizing the question here. Divided by mass A, 2250. I think you do end up with a positive answer. I think. I hope. Maybe. What'd you get? 17.1. Anybody else? Yep. So car A slowed down because it gave some of its momentum to car B, but it's still going forwards. We visualize that. Car B was parked. Car A came in, boom, and they both kept going, but car B kept going away faster. 17.1 meters per second. Direction, positive, so I'm not doing a review of work and energy. I'm kind of hoping that's recent enough. On Wednesday, if you want, you can also ask me to look at any of your unit tests. If you're thinking about doing a rewrite, I won't do that today, but I'll sign those out and collect them at the end of class. Any flex block this week, if you want to come in, you can also sign out a unit test. Folks, that is a really quick review of the course. Let me just hit stop here.